Alright, geometry, welcome to chapter 11. Compared to the stuff you just did about circles, this is going to look crazy easy. I mean, look at this title. Area of rectangle, parallelogram, triangles, and rhombi. Oh, you know what? I forgot square in there. But you know what? I don't think it's going to cause anybody any headaches. Okay, so yeah, trying to find area. It is the chapter on area. It's the first time we've ever talked about area. Area is not impossible. Area you've done before. They are kind of technical about how they start talking about area. Oh, you know what? I forgot I was going to show you this. This is what we're going to do new now. At the beginning of class next time, and it's going to be the beginning next time because this is the first section. As we get into it, it's the first section of the chapter. As we get into it, this will kind of be the second thing of the day we do. But instead of doing video questions now that I have you write down, I'm going to have you look at these now and think about this. These are the learning targets. It's another buzzword I'm going to start using now. The learning targets for section 11.1, 11.2 are these 6 things. So you might want to pause right now and take a look at this. These are the questions, or come back to this. We're about a minute into the video. Come back to this at the end. These are going to be the questions I ask you at the start of class, or always at the very early in the class. You'll want to be in your groups, and you'll talk about this type of list of questions. So just be prepared to talk about it. You don't have to answer them written down now, but if you don't have these answerable to your satisfaction, you might feel like you wish you watched the video a little closer when you get to class next time. Okay, have a look. Okay, so now you have a little bit of an idea where we're going with this whole area thing, at least so far today. They are a little bit technical. They even give you some postulates about area and about how they set it up. First of all, they sort of define area. Area is a sort of a two-dimensional space kind of thing. Like if you're going to try to figure out how much paint you're going to need to cover something, or how much carpet you're going to need to cover something, how much exposed surface there is on a 3D object. We're going to be doing that in the next unit, but it comes from this idea about what area is. It's an area of a two-dimensional space that you find, and that's why the units are things like square centimeters or square inches. Okay, you can read this. I make a little pun here, and it's really hilarious. Okay, so once we have that all figured out, you got to base your study of area on something. And again, since the area units are called square units, it's good to talk about, well, how do you define area of square in the first place? Area of square is, guess what? No huge news flash here. If I'm going to try to find the area of a square, all you got to do is, I can't believe I'm actually doing this to grown students. Alright, if I knew this was 5 and I knew this was 5, the area is, guess what? 5 times 5. And you know what, there's a reason, I don't know if you ever thought about this, but there's a reason why we call this squared. Oh, I should be saying that I'm doing area here. We call this squared because that would be the area of a square that has that side. And really, if you think about it, this is a unit measure. This is I'm saying there's 25 of something. I'm saying there's 25 of these little tiny unit squares that somehow fit in there. If this thing is 5, and I think you've seen this before, if this has really got a length of 5, and this has really got a length of 5, like a ruler, length of 5, check my math here, check my measurements. If that's really got a length of 5, I split this into 5 equal spots, and I'm saying that if I measure along that bottom edge, it's got a, now this isn't perfect, I could count 1, 2, 3, 4, 5 units, and same thing this way, and you're seeing what's going to happen here. Now, if this is painfully slow for you, go ahead and fast forward, but yeah, and these aren't perfect, but you notice in there I actually have 25 of these little guys in here. If you really wanted to count them all up, there's 25 in here. There's 25 of those little, oh, I'm actually going to dot them all. You know what, why not? I missed that one. I had 2 here. Yeah, there's actually 25, and there are 25 square units in there. Okay. Again, no big surprises there. Then the next one I talk about is the area congruence postulate. This is a little bit new, I guess. If you have 2 totally congruent figures, oh, and I can make them. I have some weird figure, I don't even know what it is. But if I watch this, computer magic, if I have 2 of these, whatever weird figure that is, if they are actually congruent, and they are because I use the copy paste function. Ooh, I use the copy paste function on my computer. The area of this weird creepy angel ghost thing is the same as the area of this one. If the figures are congruent, then they must have the same area. Okay, I'm looking like I'm really bad at handwriting here, but it's just the computer. If those things are actually congruent figures, that implies that the areas are equal. Gosh, that's really bad. Hopefully you can understand what I mean. Notice the converse of that would not be true. If you had two figures that had the same area, doesn't mean they have to be congruent figures. I think you can imagine a square and a triangle that might have the same area, but that doesn't mean that they're congruent. They're totally different figures. But if the figures are congruent, then they have the same area. Area addition postulate. This comes up when you are talking about, oh, say I have some weird figure and I don't know how to find the area of it. Like, okay, that was really weird. But say I have this wacky figure and I don't exactly know how to find the area of it, but I know enough about it to know how to chop it up nicely. Like maybe I know that this little part here is a trapezoid. Say maybe I have a trapezoid over here, and that's kind of easy to find that area. And then maybe over here I have some other, and of course I had to make one really crazy. Say if I added this on here, maybe I would know how to find this triangle at one stage, and then I could sort of subtract that from this other bigger quadrilateral. Now this diagram isn't very helpful, but basically what the additional area postulate kind of means is if I wanted to find these two areas, I knew they didn't overlap, I could actually add them, and I'd get this, I'd get an area that was something like this. In the book, you're going to get questions like this. I gave you this like crazy little shape where everything is 90-degree angles and everything's nice, and they're going to ask you to find the area of this wacky thing. Well, if you wanted to, you could cut it into rectangles that might make sense, for example, and you could find the area of all these rectangles separately. Find that rectangle, find that. And as long as they don't overlap, it's okay to add those, and you will actually get the area that you want. That's all that's about. They're just spelling it out, technically, because this is a geometry book. Okay. And we had the same type of thing when we added segments. They gave you rules about when you can add lengths. They don't overlap. They share sort of a common endpoint in the middle. Same thing with angles, and we just did it with arcs. Okay. So then the rest of this is just a bunch of formulas, and I'm pretty sure you've all seen these before. There's my sarcasm here. Like if you need to know the area of a square, guess what? It's that times that. If you need to know the area of a rectangle, it's that times that. And that gives you an answer in square units that converts sort of this space area in here to saying how many little squares fit in there. And of course sometimes that can be fractional and it can be really bizarre. Pretty soon it's going to be irrational. We start talking about circles, but that's not in this first section. I'm already into the 11.2 now. I'm trying to save time for you here. I'm still under 8 minutes. Area of a parallelogram. This is kind of cool, actually, and we're going to do this in Sketchpad in class. This little thing I just made here about quadrilateral or about parallelograms is kind of like the thing you're going to do in the Sketchpad in class, but I just made this little rectangle ABXY, and I'm going to compare it to the area of ACDB, that's the purple one, this is the gray one, and I can wiggle this around and it'll change, of course, but if I set this up so it's exactly there, it shows you that they're both 17, but watch what happens when I slide this straight over. If I leave it right on the line there, it's also 17. If I can just leave the, of course, I'm wiggling a little bit, but just trying to illustrate here that the area of a parallelogram, of course I drop it right there and it's off. Area of a parallelogram is the same as a rectangle that has the same base and the same perpendicular height. So it doesn't matter how far down the line here I move this. This is still 17. I can even move it off over there. It's still 17. How far I make this, if it's the right height, it should be 17. 17. If you look at, say, something like right here, that is 17. If you look at the area of this sort of darkened rectangle, I think you can believe it's the same as this purple parallelogram. See the part that's missing over here that's been chopped out of the parallelogram? I could sort of pick this up and replace it right here, and it fits in there. Basically, the height doesn't matter as long as the height's perpendicular. It doesn't matter sort of where this shadow is falling. This little triangle is going to fit inside here, so that the entire purple thing and the entire gray thing are always going to have the same area. And this chapter is just a whole bunch of stuff like this. So anyway, parallelogram area is just base times height. Triangle area, I think you've seen this before. It's base times height times half. I just showed this little shadow here, shows you really quickly that, and I try to make it look like this parallelogram for a reason. This triangle is supposed to look like, because it is, exactly half of the parallelogram it fits in. That's one reason why you could say it's half. Notice in all these, I have height and base, height and base. I have height and base in these two. the book's definition, or the way they use the terms height and base, they're very technical about that. You can't call it a height and a base unless those two things are perpendicular. So I'm showing you that here. This base length is this whole length from here all the way to this part of the triangle. If I use this entire base and this height that's perpendicular to it, I will find, and the half, I will actually find the area of that entire triangle. If I just measured the base to here, this base times this height would be the area of this triangle here, which is also how you find that. But what I meant by this is any triangle in general, if I know this entire side, and I know the length of the height, the perpendicular distance from that line to this point, which is always something that's defined, that's how I can find the area of a triangle. There's only one left. It's the rhombus. Of course, all these things are listed in different theorems if you care to look them up. But the rhombus could be figured out two ways. First of all, you could do base and height, because after all, a parallelogram, or sorry, a rhombus is a parallelogram. But also, you notice in a rhombus, gosh, I keep saying the wrong thing. In a rhombus, there's always going to be a right angle inside here. Here's the actual GSP I used to make these things. Can I actually measure this angle like this? Oh, I can. Notice it just snapped it to a right angle there. There's a right angle here at the center. So let's get that out of the way for a second. This little triangle here, B to the center to D, let's call it something, BHD, that is actually a right triangle, and the dimensions of that are half a diagonal and half a diagonal. And if I go half a diagonal times half a diagonal times half, that would be the area of this bit in here. And I get to multiply that by 4, because I know all 4 of these are the same. This little piece is the same as this little piece because it's a rhombus. This piece is the same as this piece. I have all kinds of congruent triangles everywhere. So finding the area of the entire rhombus is just adding up these 4 non-overlapping triangles, and they're all congruent, and it's very easy to do that algebraically. We'll go over that proof in Sketchpad in class, and I'll discuss why it is what it is. And it's this nice little algebraic demonstration. Anyway, I don't need to waste more of your time. This is an extremely straightforward couple of sections about the areas of these 3 or 4 or 5 things. Square, rectangle, there you go, parallelogram, triangle, rhombus. And the most interesting thing, I guess, is the fact that you can find a rhombus in 2 pretty straightforward, easy ways. You could either use height times base, just base times height, or you could do half of this entire diagonal times this entire diagonal, because it is actually also 4 right triangles easily measured by the length of the diagonals of the rhombus. Okay, I'll let you see this one more time. This is the questions you're going to have to answer. I think I've spoken to, okay, I can't do this with this. I got to do it this way. I think I've spoken to all these pretty well, and I will see you in class.